Hey guys, so today let us look at GLTF files. What's a file format? What data is present in the GLTF file? And how to use the data to render the models in VSPS pipeline, which is the simplest, then mesh shading, and then ray tracing. And we'll be looking at dear.gltf, which is like kind of the hello world of GLTF because it is very simple. So what data is present in the GLTF file? Let me just bring up my dear sample in wireframe mode to visualize, what data outputs what. So firstly, we have the vertex data, which is the position. So the position data combines with the model view projection matrix in the vertex shader. If you are using the legacy vertex shader pipeline, VSPS pipeline, and then that gives the shape of the rear. Then we have normals, which is used in lighting calculations. I don't have a light right now, so I don't use normals, but I plan to do it this week. And then we have text cards. So text cards combined with materials to give the texture of the rear. So all these pixels, the yellow horns, the skin color is read from a file, and how to splat it on the deer is given by the UV texture coordinates, and then indices. That's a bit interesting. So, but basic. So if you see this vertex, it's shaded by many triangles. I think five, right, or six. So we wouldn't and the the way the pipeline works is we need to give it a list of triangles. So instead of repeating this one triangle, this one vertex for all these triangles, we just the vertex buffer has one entry, and then the index buffer indices as many times as required. So I think we covered everything. We have all this data present in the GLTF file. So let's look at a very simple GLTF file, my favorite, dear, which is the hello world of GLTFs. So the GLTF file is a hierarchy of different what do you say different data. The way I understood the GLTF is going to the bottommost to the leaf node where the actual data is present. So we can this is an array of buffers. In this case, we just have one buffer, and this is the binary data encoded in base 64. And we have around 1 MB worth of data. Now, if we so this particular data blob has all this information, and if we go up, we have something called buffer views. So the buffer views split the the entire data blob into logical chunks of various sizes at various offsets. So, so when we read the buffer views, we know how to divide the entire data into 1, 2, 3, 4, 5, 6, 7 logical chunks. But still, buffer views give a very raw representation of the of the chunks. We don't know how to interpret the data yet. For that, we go one level up and look at accessors. So the accessors specify which buffer view to look at and what is the data format. And this is specified in the GLTF spec. So if we want to look at what is 5126, GLTF processing libraries have convenience functions or macros defined. So I don't get it here. I don't know why. Sometimes I get it and sometimes I don't. I need to fix my search. Anyway, so let's go to the tiny GLTF folder, and then we have all these data types. So 5126 is float, and float is always 16-bit float. GLTF, sorry, 32-bit float. GLTF does not have a definition for 16-bit float. So So this is a float of three vec3, meaning uh, three floats are bunched together. So when we read this buffer view, the way we want to interpret the raw bytes is as float 3, and in our directx the format is R32, G32, B32 float. And similarly, we have buffer view 1. Again, I think this is position data. I think this is normal data. Then since we have float 2, uh, float again, everything is float. And then vec2, float 2, meaning I think this should be UV data because UV is generally XY coordinates. And then this is scalar buffer view 5. So this must be index data. But at this point, we still don't. We know how to interpret the raw bytes as float 3 or as scalar or something, but we still don't know uh, w- what type of data it is among this this set. And yeah, this is 5123. So if we go to 5123, again we have 5123 defined as unsigned short, which is a 16-bit integer. So in our TX world, we have its R16 uint, so it must be indices. But if you go one level up, this is where the entire description lives. So now this part of the GLTF file gives us what is the data, how to divide it into logical chunks, and then how to format each logical chunk. Now, before going to meshes, let's see how to read the GLTF file from the top. So from the top, the GLTF file has a scene, and scene is an array. So when you see scene 0, come into read the first part, and each scene consists of nodes. And again, this scene has only one node, which is 0th node. So we come to the nodes and read the 0th node, and the 0th node has each node has a mesh, and the 0th node has only one mesh and a name. And this is not important right now. Each node has a matrix, has a model matrix, translation, rotation, and scale. So in this we have only one mesh, so it's not much useful. But say you have a car with four wheels, then we'll have four meshes, and we need to use the scale, rotation, and translation to properly construct the car. So we need to use a model matrix and then construct the meshes and place them appropriately. So this information is required for that. Anyway, so this node refers mesh 0. So now we'll go to mesh 0, and this mesh is what we see here, the deer mesh. Anyway, so this is what we see. So it is okay. So let's see how do we read this. Once the GLTS spec says is once you start reading primitives and once you start reading attributes, each attribute is a name followed by a number, and the number indexes into the accessors. So when you see position 0, that means the position data. You can access the position data by going through accessor 0, and we already saw accessor 0 specifies float of vec3 format, and then we can go down and access the raw data, and this is how we build the vertex buffers. And there is this one bounding box which I don't use right now, and I'm not sure why we should use it, but for now I'm ignoring this. So similarly, we read the position data, the normal data, text coordinates, and indices. Again, it's a GLTF spec which says once you see indices, go to whichever the accessor which is specified here, which is accessor 5. So this is access. This is how we read the index buffer and construct the index buffer. And then materials is a bit tricky because it has always been tricky for me. Geometry is still simpler. But anyway, what the GLTF spec says, once you see material, uh, index into the materials node. This is material 0. So we have material node here, and the material information is present here. This is the culling information which says that both sides of the triangle needs to be visible, and then just a name. And then here we can have PBR metallic roughness gives the actual color, the deer color, but we can have multiple nodes like specular and emissive and all those things. I'm not very even I need to learn about those because shading is one thing which I kind of ignored till now, but I think I should get a hang on. But anyway, so what do we see here? This this particular PBR metallic roughness has a base color texture. So the text code here indicates that we need to use text code 0 as a UV when we read this texture, and the index 0 indexes into the texture node, which is this part of it. Now, this texture node has this doesn't have it, but this texture node can have two things: sampler and an image. So since it does not have the sampler, we'll be using the default sampler. We should be using the default sampler. And then the source 0 says go and access the image specified in this index refers to the images array. So now this images array says, okay, my data is present in buffer view 6, and it's of PNG format, and the name is deer. So to create the texture data, we just go to buffer view 6 here, buffer view 6, and interpret this part of data as a PNG image and load the texture. So it's as simple as that. No complications, nothing. So let's just, what do we do now? Let's just go to get a pix capture and see how it all fits in a simple VSPS pipeline. For that, let me just show the next slide also. We just run this so that I can get the exe name to get the pix capture to visualize the data what we have. So, oh yeah, I included some camera things so that I can do this, but anyway. So going back to the slides, so in the VS, so I am stressing this because in each of the pipeline, how we read each part of the data is very different. In the VSPS pipeline, uh, that is in the Hello World in the sample apps, uh, the position, text code, and normal, that is this part of the data, position, normal, and text code go into the IA layout. So what is IA layout? Let's, I don't know what capture is this. Let me just close this. Okay, this is ray tracing. We don't want that now. Launch and see, I forgot to copy the exe name. So let's take the exe name, plug it in here. Pix is very useful to for functional debugging, performance, and even for learning. So once you get a capture, you start the analysis, and let's analyze the capture. So this is something called as a frame VB, which my sample app uses to compose the final frame. It's not related to GLTF. Next, we are reading the position buffer. So as I was telling earlier, how I create the buffer, I go to position and then read 0, 0 meaning I need to go to accessor 0, and then in accessor 0 I access the buffer view 0's data. I go to buffer view 0, and then in buffer view I know this is a position data, and then I just create the buffer. So as you can see, this is the data in the buffer. Since it is position, we should interpret as float 3. So we have all this as the position data, and then nothing fancy, normal similarly, and then text card, and then yeah, text card 0, 1, 1 and 2, and indices. The interesting part which you can actually see visually is the texture. So this is the deer texture. I think these are the horns and these are the body parts and these are the hoofs. So the UVs actually help to map this on the body of the texture of the deer. So anyway, let's look at draw indexed offset. So if you can see 107, so this is the index count. Where do you get the index count? It is specified in the accessor of the indices 10764. So 10764. And if you can see, the vertex count is smaller. So as I was telling you, there are old triangles share vertices. So the vertex comes only once, but the index, we go and index the same vertex multiple times. So that's why we have more number of indices. So 10764 indices index into 2440 vertex buffers. So okay, in the vertex, in the VSPS pipeline, there are two sources of data. The first one is the IA layout. So Dx12 gives APIs like IA set vertex buffers, IA set index buffers, and we define the IA layout. We set the index vertex buffers and the index buffers, and then we just tool draw. So the vertex shader is invoked 10764 times. It transforms all the vertices using the MVP matrix, using the camera matrix, and then we go into rasterization, and then the pixel shader uses the texture to shade it. So anyway, I come to this. So yeah, so the input to the vertex shader is to the IA layout, and the input to the texture is accessed via root signature and root arguments. So you can see this here in my root signature. I have the camera matrix, and the camera matrix is also accessed during using root signature. And sorry, and the shader resource view, which is the texture. So we have two ways of accessing the data. So if I go back to the slide to this part is accessed via IA layout, this part, and this part is accessed via root signature, the root parameter, the root arguments, in addition to the camera buffer. So this is what I was talking about. So this is how it looks. Root signature is a bit complex. It took me around, I watched a Microsoft video for around 7, 8, 9 times before I could totally understand, totally understand it. So the root arguments are composed of root constants, root descriptors, and descriptor tables. And this is the various data my sample apps use. Okay, so I wouldn't go. I'm just focusing on how data is accessed in different pipelines. Right? So this is about VSPS data. Now the mesh shaders. What happens in mesh shaders? So mesh shaders are more recent and they're more advanced when and I think most of the graphics content on desktop will move towards mesh shaders. So the whole IA layout is taken out. There's no IA layout anymore. So that means we need to understand how to access this data because previously this data is being accessed using IA layout. So in mesh layout, there's no IA layout. There's only one source of data now, which is the root signature and root arguments. So that is, let's go to mesh shader. As you can see, the data, the input data is same, the output is same, but what happens in between is completely different. It's everything is same. So let's see how does it look in pics? How does it look different to the traditional VSPS pipeline? What I'll do is I'll just take hello world and I forgot to save it. So okay, let's just keep it like this. And now I'm going to launch the mesh shaders and launch. Oh, it replaced it. Okay. Anyway, so let's see how this looks. Let me just confirm that this is mesh. This is in fact mesh shader. Yeah. So anyway, so as usual, my composition buffer and then my position data and normals. And if we scroll down, I have the same texture, the deer texture, and the draw index is replaced by dispatch mesh. Now, how did I arrive at 64? Here we no longer there we said okay draw 10,000 indices, but here it no longer works that way. We need to divide the mesh into meshlets and divide our work into the dispatch size and the work group and the local thread group size. And anyway, so we need to calculate on how much is required to draw the complete mesh. That depends on what you do on the shader, and I spoke more about all this shader in my other video where I debugged the mesh shader to give the proper output. So anyway, here we are focusing on how do we read the data. So if you see, there's no IO layout. The IO layout is taken out, but we still have root signature. So the entire data, there's only one source of data, which is the root signature, which is this. So let's see what are the root parameters. I have root parameters. I have the CBV, which has the Camena data, which is here. And then I have the root descriptors. I have only one descriptor table, and then sorry, descriptor table as the second root parameter. The descriptor table, if you remember in the VSPS, I had only one SRV bound, one texture bound. Here we have four. Now, why do we need four? We want index buffer, position buffers, text code buffers, and the texture itself. So if everything which was bound using IA layout is taken out from here and makes its way to the root signature. And in the traditional VSPS pipeline, it's kind of hidden from the developer. The GPU driver and the GPU takes care of propagating data from the set IA layout calls to the vertex to the vertex shader. Here, if you see the shader here, the app developer has to bind the index buffer, the uh, the position. So the vertex buffers are divided into, you see here, the vertex buffers are divided into position, which is the actual geometry, the text chords, which are required to texture the sample. So we have to bind, the app developer has to bind these as structured buffers or raw buffers, and then based on the thread group ID calculations, we need to access the index buffers, the vertex buffer, and then the rest of the pipeline stays the same. There's a rasterizer here, And then the pixel shader is exactly same as our previous vertex shader, pixel shader pipeline. Only the geometry stage is completely different. So this is about mesh shader. Then next thing is ray tracing. Even ray tracing is very new. It's in active research and development. I think VSPS 15 years, last 15 years, 20 years. Mesh shaders maybe last 5 years. Ray tracing I would say maybe last 4 years. It's like both of them came together kind of in my view. Maybe I'm totally wrong. You can, but these are the approximate timelines. Anyway, so in ray tracing, we can kind of say we have two sources of data. So let me just start a project and then ray tracing. This looks the output looks the deer looks the same, but the background is different. And as I mentioned in my debugging ray tracing video, the background is actually the direction in which the rays are shooting. So as I change the as I change the deer direction, it the direction in which we shoot the rays are different. But anyway, so let's see how this looks in pixels. Do I have the exe name? Yeah, do have the exe name. So let's take this and let's go to pix. Okay, let's start the analysis and say, okay, what's happening here? Okay, so as usual, I have my frame vertex buffer and I'm loading the position data, blah blah, and then I'm loading the text chords data. Okay, good. This kind of looks familiar. And then you have the texture data. Yeah. So the first difference we see is something called build acceleration structure. Here I'm building the bottom level acceleration structure, and here you can see position and indices. So if we go back to the slide, so in ray tracing, this is the acceleration structure which I talk about, where all the geometry, only the geometry portion of it, that is, this part of it goes into the acceleration structure, and of course we need the indices to make sense of the geometry data. So the indices and the positions go into building the acceleration structure. So there's no I layout again. I layout is taken out, but now we have the position data building the acceleration structures, and then we have everything else comes in the root signature and the root arguments. Just note indices. So what do we have here? As usual, I have my root CBV, which is the camera data, and the root descriptor table has the texture where the deer texture which we see here, which we saw earlier. Anyway, I can show here also. So anyway, okay. So this is a bottom level acceleration structure, and so we can actually see the result, and we can see the yeah, okay. This camera is weird, but anyway, we can see, there's some geometry here. There's no texturing, nothing, just the geometry information. And then we have top level acceleration structure. So the top level acceleration structure takes the uh, takes the model part of the matrix. So I didn't stress earlier much because model view projection matrix is an entirely different concept altogether, and I don't want to uh, put it out in this video. But the core thing to understand is in VSPS pipeline and mesh shaders, the model view projection matrix is one, and it is used together in the shaders. But here we split it up. The model matrix goes into the top level acceleration structure, and it references the bottom level acceleration structure. And in the shaders, we just use a view projection inverse matrix. But anyway, that's something different. So yeah, we build the acceleration structure, which is the geometry part. And then if you go to dispatch rays, So as I said, there's no IA layout, so we have our root signature, and if we just look into it closely, we have a CBV. Then this is my second root parameter where we have three SRVs. Is it three? Yeah, I think. Sorry. Yeah, two SRVs. So what do I have two SRVs here? Hang on, no, it can't be. Yeah, there are two ranges. So the descriptor table has two ranges. The first the first range is SRV, where I have my three SRV. So what do I have here? I have the texture coordinates, the UV, the texture itself, the texture coordinates, the UV coordinates to help us map the texture. And then again, we have indices here because whenever we need to access any vertex buffer, be it position or text chord, we need the indices. So here the indices are required to indices into position and build the acceleration structure. Here the indices are required to index into the text chord buffer and texture correct and sample the texture correctly, right? Okay. So the shaders are completely different because here we end up shooting a ray and either missing everything or hitting everything. I spoke a lot about this in debugging ray tracing, so that can help make sense of how this whole shader thing works. But the core part is even here we need to access the index buffer, the UV buffer, we need to get the barycentrics, interpolate, and then access the texture. So, but here one difference is in ray tracing, the root signature is divided into global root signatures and the local root signatures. So the reason is the entire geometry is present in the acceleration structures. In this case, only the deer, but you can have an entire scene in the acceleration structure. So we need a table of shaders, a table of root signatures so that each geometry can access its own data. Uh, for now, for this simple deer, I'm just using a global root signature. But as I keep progressing, it'll get very it'll get unmanageable if I put everything in the global root signature. So I need to use local root signatures, which I'll be doing as I make more advanced samples. So I hope this helps. So to give an overview, what we covered is what data is present in the GLTF files and VSPS pipeline, how the data consumption is split into IA layout, which is the geometry part, and the root signatures, which is the texturing part. And in mesh shaders, the IA layout is completely taken out, and the geometry data is also read through the root signatures along with the texture data. And in ray tracing, the data is consumed way more differently because now we have the the position part vertex uh, of the vertex buffers are consumed in the acceleration structures to build the geometry, and the the other part stays in root signatures, and the root signatures are divided into global and local root signatures, which I'll talk about in my later videos as I build more advanced scenes. So I think I covered everything what I wanted to. Oh, just one thing. Here we need to this acceleration structure. We need to bind it as an SRV buffer in the descriptor table. So that's why we have SRV acceleration structure. So that's how we shoot the ray into the accelerate. The region shader is able to shoot the ray into the scene acceleration structure. And one more thing is even the UAV. I forgot to mention this. Here we have two descriptor ranges. One is the SRV, and the second thing is the UAV descriptor range. Where is the UAV descriptor range? Yeah, descriptor ranges. This is 0 and this is 1. In the first descriptor range, we have the UAVs. And because the output here is written to the UAV. I didn't speak much about the output, but in mesh shader and in vertex shader, pixel shader, we write the output to an RTV and a DSV. Here we don't have a DSV, we just write it into a UAV. And that's it for now. Thanks, guys.